Hello friends, we are going to start the compiler design, in which the first lecture, which is lexical analysis. The weightage for the gate exam is very less, but which will give you insight into the compiler design, how we begin the whole program while scanning how the tokens are recognized in the lexical analysis. If you look at the weightage of the compiler design in the gate, which will be varying from 4 to 7 marks in between. So average of 5 to 6 marks you can predict from the compiler design, but sometimes 7 marks, sometimes even 4 marks we can predict from the compiler design. Okay, in this compiler design, we will be learning lexical analysis, and I will help you to learn syntax analysis, then syntax directed translations, then intermediate code representations, then code optimization. Okay, so which will be covering the overall the weightage around 4 to 7 marks, which will be predicted in the exam. 4 to 7 marks. In some of the years you will see 5, 6. The most of the years you will see 5 or 6 marks. Unpredictable marks like sometimes 4 and 7. They are unpredictable, but still we can guess it may happen in future. Okay, let's start with the lexical analysis. But as we are beginning the compiler design, first you should learn the introduction to the compiler design, then we will move to the lexical analysis. What is the introduction? What we are going to learn in this introduction? The compiler is the collection of phases, right? How these phases are going to work in compiler. Before that, first let me help you some of the few concepts. Mainly, if you are going to give a C language or C program, you are going to use C language, right? How this C language or C program is going to process from high level to low level. So the C language, the processing system we will be learning first. Then we will move to the main topic, which is the phases of compiler. In this we will be learning like lexical, syntax, semantic, various phases we are going to learn in the phases of compiler. Then if you are interested, we can also look at some of the errors and also symbol table. Many things are there. Then we will move to lexical analysis. Okay, let's begin at the first, how C language is converted from high level to low level. Very simple. You give a C program which is high level language. This is high level, right? High level code. Where do you give? You give to, let's say, you do something here, it will convert to the machine code, low level code basically. Maybe you can say executable machine code that you want to convert. Then how many components are involved here? The various components are going to be involved here, various components. We're going to learn some of them here. So let me help you again. You give C program, the first component which will be involving editor. Where you write a program, so C program you are going to write an editor, right? So once you write or edit the C program, you will compile. So while compiling, what happens here? I'll put a boxes, you try to understand what's going to come into the picture. So here there are many things. I'll put one box, but actually it may not be one box. Okay, here preprocessor, then compiler, then assembler, then the output will be produced somehow, and again here the two things might come here, and then you will see the actual executable code here, executable machine code. Very interesting, right? So many things are happening, but we don't worry about all these things. Just write a C program and do build and run or compile and run. You will see the output, or you will give an input, you will see an output. Okay, let me write some of them here. The first thing is preprocessor, right? Preprocessor. Then compiler. Here assembler. Here linker. And also loader, linking and loading purposes. Now, what is happening here? You give high level C program. Let's say you are writing some program here. You're writing some program which might be having one declaration, and you might be having some assignment, you might be printing or something else. And somehow here executable machine code, you don't see, you see just zeros and ones. Don't know what actually it is here, but it is going to run something. This is going to be your file. So somehow it's converts, right? And during this conversion, so many components are involving here. How they are going to convert into various, you can see various outputs, like pre-processed output, and assembly code, and then relocatable machine code, and so many things are happening here. When you look at the editor, once you edit your code, then you start compiling. This whole stage of compiling, right? This is a complete stage of compiling, and this linker and loader, it might be part of compiling and also in the part of execution. So this thing is a static and dynamic. It's a hybrid model, right? But these stages are static stages. These stages are compilation stage as well as runtime stage. Now there are many things, as I said. So what's this preprocessor? We'll be learning one by one, right? As we are not hurry about understanding the conversion from C to executable code, we'll learn one by one, and remember simple definition for each component which is here. What is the preprocessor? Okay, you see there are many statements in preprocessor. Then what are they basically? You have come across hash include, right? This is called as preprocessor statement. It's a directive statement basically. Sometimes you have seen hash define, max 100, something like that. Okay, there are various preprocessor statements. Even you have hash if defined, if not defined, hash else, and if. So there are so many preprocessor statements are there, right? I'm just taking two examples. What is the speciality of these statements? These statements begin with the hash, and this can be written anywhere in the C program, but we do always mention in the beginning of the program. Okay, but any statement which begins with the hash are called as preprocessor statement. Here this preprocessor is going to do something. It takes the C program which has the preprocessor statements, then it does something to them to convert into the pure C program without the preprocessor statements. So you give C code, the preprocessor understands all the statements which are beginning with the hash, and it does something to them. It produces preprocessed C code. It means it's going to do something for that preprocessor statements. Okay, so this hash include stdio.h is another file, right? Another file, it need to be linked, so it gives some information to the linker, so that the linker understands, okay, there is another file this file is going to depend on, so that when you use the printf and scanf, it's going to look at in some library file which is already have a reference here. And this hash define max 100 is does by preprocessor. Wherever you see the max constant, it's going to replace with 100. Is it clear? That max whole program it's going to look at and replaces with the 100. So it's a very important these two statements or any statement which begins with the hash is going to be understood by the preprocessor. It does something to that code so that when the compiler sees the code, there are no preprocessor statements, so that it can analyze using the various phases of compiler. When you look at the practically, the preprocessor is also part of the compiler. So when you scan the whole program, the lexical analysis and preprocessor both are going to come into picture and they invoke it. Okay, so don't worry much about the internal implementation, but remember the preprocessor is the first stage during compilation, first stage during compilation to understand all preprocessor statements. So what is the preprocessor statements? Any statement which begins with the hash. In C language, all the preprocessor statements begins with hash. If the preprocessor do not understand, it will produce an error. Any statement which begins with hash is called as preprocessor statement, or you can say directive statements, directive or preprocessor command or statements. This is called as a macro. This we defined a macro max. So this is called as macro definition. Fine. Conditional macros also we have, like hash if, hash in, end if, hash else. Like you have so many macros in conditional macros in C language. So this is about all preprocessor. When you write a C program, first you understand, you means the system understands, compiler understands the preprocessor statements during preprocessing stage, then it comes to the compiler phases. As we are talking about compiler design subject, there we don't involve much about preprocessor. We involve from lexical analysis to code generation, all the phases, right? But this preprocessor understand the definition, what is happening here. We can include the files, we can define new macros, and we can have conditional macros to check whether the macro is defined or not. That things can be done with the help of preprocessor. Okay, so now a very simple program for you. Like I have hash define, I'll just write a sum of course looks like a function, but it is not a function. Okay, x plus y. Do not write semicolon at the end of the statement. This is not a C statement, it is a preprocessor statement. Normally C statements ends with the semicolon, but directive statements do not end with any such semicolons. So do not use semicolon at the end of this preprocessor statement. And spaces, everything that you do here is very important. If you are going to include the spaces anywhere, it's going to produce the error. Remember, it will not allow to compile because preprocessor is not going to understand it. So do not include the spaces anywhere you like it. So as per the system, as per the preprocessor syntax, just follow it. Okay. Now I am going to do something here. Let's think about this statement. I'm going to do here some expression. A is equal to B is equal to 5 and C is equal to 0. Okay, don't worry much about it. C is equal to sum of x comma y multiply with, oh sorry, x is not there right here. Here a comma b multiply with sum of a comma b. Okay, and then I may print the value of the result. The result is, let's say, decimal value present in C. Okay, now try to understand the output of this program. What is the input that you have given? Nothing. Already the data is available within the program, so there is no input. Input is already taken within the program. Now what is sum of a comma b? A is 2, B is 5. Will it be returning 7 or 2 plus 5? Both are different. Remember, replacing with 2 plus 5 is different from 7. What is the difference? If I am replacing 2 plus 5, that means I am doing copy paste simply without evaluating. But if I am replacing with the 7, that means I am taking 2 plus 5 and evaluating, then 7 I am putting here. So what should I put, 2 plus 5 or 7? So what preprocessor does, it does not evaluate any expression that you have. Here this is an expression, it's not going to be evaluated. That means it just text, it assumes it's some text, it's going to replace it simply. So x plus y, that is you pass 2 comma y, 2 comma 5, 2 plus 5 is going to be replaced in sum of x comma y, that is a comma b. Now here what happens here, especially what happens, it's going to be replaced with 2 plus 5, that's it, and this will be replaced with 2 plus 5. So this expression, especially this one, what happens here is c is equal to 2 plus 5 multiply with 2 plus 5. This is an expression seen by compiler. Okay, compiler is going to see this statement, but preprocessor is going to see this statement. It's going to replace with 2 plus 5. So when it comes to compiler, the compiler knows that only 2 plus 5 multiply with 2 plus 5. Now compiler can decide what to do. Right? If the preprocessor doesn't come here, the sum is actually not a function. The sum is the macro here. You can see that. So it looks like a function arguments, but it's not a function at all. So the preprocessor is going to come here and replaces sum of the 2 comma 5 with a comma b with 2 plus 5. A and a is 2, b is 5 already. So it's going to take care of that. Fine. So this is the job of a preprocessor. This is the job of preprocessor. So what it's going to do, sum of a comma b, will it replace a plus b or 2 plus 5? That is also important. When you look at here, I'm just going forward and I'm explaining the values, but in between if the values changes, it will also change. So instead of this 2 plus 5, the sum of a comma b, it's going to replace with a plus b. That's it. If you pass 2 comma 5, then only it takes 2 plus 5. Otherwise, simply a plus b. So this is actual replacement of the preprocessor. C is equal to a plus b multiply with a plus b. Then when it replaces with the 2 plus 5, if you write a macro sum of 2 comma 5, then it will replace with 2 plus 5. Here I am not doing it any evaluation. Preprocessor will not understand what is the value of a, what is the value of b. It just does. You have given a comma b, does a plus b. You have given 100 comma 1000, 100 plus 1000. That's it. The job of this macro. Okay. So that is all, the what preprocessor does here. It's not going to understand more in detail like a compiler. Compiler does something to understand like syntax check, semantic check, but preprocessor don't do that. Preprocessor just replaces what is here and what is going to be replaced. So this is called as a constant and this is called as expression. Okay, it's a macro definition. Now you tell me what's going to be the result. A is 2, B is 5. So compiler, once you compile, then at runtime the A value is 2, B value is 5. The system understands how to evaluate because compiler already disclosed how to understand. So compiler, what it does is there are arguments, there are precedence rules. Using those precedence rules, there is addition, there is a multiplication. So it takes a priority for multiplication. So it does first multiplication. What compiler does is first B multiply with A does. Once it does, then you have A plus B, result plus B. And now there are two additions. After doing multiplication, there are two additions. And also there is assignment. Assignment will be done at the end anyhow. So now two additions are there. How these additions performed? Which addition should be done first? C plus some result or that result plus B? What is going to be done? In C language, the two plus are actually having equal precedence. So it follows left to right. It follows left to right. So now the who is having who is the left plus, that's going to be evaluated first. Then this A plus, the result is going to be evaluated. Then with that the another plus, because equal plus only the next two operators. So this plus is going to be done next. Then after that the result will be assigned to C. This is how going to be evaluated. Now if you look at the result 2 and 5. So 5 here. This is a 2. Let me write that. A is 2, B is 5 and multiply with A is a 2, B is 5. This is going to happen, right? So what is b multiplied with a? This is going to return 10. And then after that, a plus, that's 2 plus 10, that's a 12. Then 12 plus 5, that's a 17. So c value is 17. So here the output comes as value is equal to 17. Okay. Then where is the problem? Problem is what you might predict, that's 2 plus 5, the 7 might be returning. What happens if 7 is returning? 7 multiplied with 7, which will be 49. But where is the 49 and where is the 17? So huge difference, right? And when will be returning, when will be happening that in place of this x plus 5, if you give this parenthesis, then definitely the same parenthesis will be put, then a plus b, the 2 plus 5 is evaluated first, because parenthesis having more precedence before applying any other operators. So it's very important, if you have certain things, you might be evaluating 2 plus 5 first. So you should know, that's what the compiler required for you. Somebody writes an expression, the compiler takes a decision where the precedence is considered, because already the compiler has some precedence rules, and following those precedence rules, the expressions are going to be evaluated at runtime. So before runtime only, compiler gives all information to the machine, which operator should be considered first, which else is considered next. Okay. This is about the preprocessor. Now I hope you understood, preprocessor is not going to execute, but it's going to replace this statement with a plus b, and this is going to impact the output that you see at the end. That value is going to be 17 once you compile and run this code, and this is going to be 17. Okay. But this job of the preprocessor job is to replace this constant with the expression as it is without evaluating an expression. Okay. Without evaluating an expression. Fine. It's very important. It's going to be placing 2 plus 5, not 7. Okay. So both are going to be different. Putting a plus b, putting the result of a plus b, both are different here. Okay. Now you got to know preprocessor. It takes the C code and it analyzes all the directive statements. Then it gives you the preprocessed C code. So you don't see any preprocessor statements now, so that the C code can be understood by the compiler. So what's this compiler? Compiler has many phases. We will be learning them. Do not focus much on that. It is also C code, but you know that it's already preprocessed one, and this C code is given to compiler. It's a compiler, and it produces, let's say, assembly code. Do not include assembler inside, just say assembly code. Example, if you have something like x is equal to 10, here it might be happening something. If you are aware of it, okay, not, then just ignore it. Like move, maybe some location, it's going to put the data 10. This is the assembly instruction, right? Every the whole C program will be converted into the assembly program. What is the compiler job? Compiler job is to understand the C program and convert into assembly program. But you also know the compiler is executing its own program. So it's a program that takes a program and converts into another program. How beautiful it is, right? So this is the beauty of compiler. It is executing some program because it has own power, and it takes somebody which you want to convert into machine code or assembly code. So it understands all C code and processes something and gives to the it converts into assembly code. Okay. So to do that, how this compiler actually understands the C code, right? C code, you write functions, variables, if statements, for statements, all the statements it understands. It understands its syntax, it understands the semantic, and it converts into the corresponding assembly code. Correct? So to do that, it has various phases. We will be seeing soon, but let me write some of them here. Here there are many phases, like you have lexical analysis, then syntax analysis, then syntax direct semantic analysis, then intermediate code generation, then code optimization, then code generation, then code optimization, and that's it. Total you will see 7 phases to convert the high level code to the low level code. High level code to low level code. this boxes I'll be disclosing once we see the introduction. In the introduction, you do not require, right? So at the end of the introduction, we will be seeing after this C language processing system, we'll talk about the compiler, what are the phases and how it produces an error and what are other things required to understand or to analyze this code and produce the assembly code. Fine. So these are the, this is the thing that we are going to do, and compiler produces a syntax error whenever it has seen some errors. It also produces special errors, that's the compilation errors. Like lexical, syntax. Mostly the syntax or favorite here. Remaining compiler decides how to produce, right? Mostly we will focus on syntax and some are semantic, but lexical is very special here, we will be seeing in the first chapter. Okay, this is all about compiler. The whole subject we are going to just look at inside this compiler and different phases of the compiler. Okay, we will come back, don't worry much about it, we'll come back. Next, assembler. Okay, we don't deal much about assembler, as you know, we are talking about compiler. Just we'll talk about, simple assembler definition. We don't go in detail about assembler like one pass assembler, two pass assembler, the various types of assemblers. We don't look at, we'll just look at we give assembly code or assembly program. This assembler analyzes this assembly code and produces machine code. Of course, to do that, the assembler should have the knowledge of many things, because this purely depends on the machine, and every machine the assembler is going to be different. So you don't remove the assembler and you don't install that way. Assembler is fixed once you buy the system, right? Because once you design the architecture, once you have the architecture of the system, then this assembler already fixed, because you can't change the assembler to the machine. Every machine has a fixed assembler to understand its own assembly language, because it purely depends on the machine. Okay, but compiler you can install whenever you require it, and but compiler also depends on assembler depends on the machine. Indirectly compiler depends on the machine, because compiler has to produce assembly code, and assembly code varies machine to machine. Okay, now what's happening here? Let's say move, previously I was writing something like, right, 1000 comma 10. Then what this assembler has to do? It has to convert the whole instruction into zeros and ones. Like I'm just writing x, but this x is nothing but either 0 or 1. It's going to convert into something like this. The x is either 0 or 1. Okay, what might be happening here? It has to understand, assembler is going to understand what is this opcode, corresponding mnemonic code, and it's going to be operation, right? What operation it is, what is the corresponding binary sequence for this? It might be allocating some sequence for this opcode, corresponding opcode. This operation has some mnemonic code, it's going to replace with that. And here, and this whole instruction, right, it's an instruction. This instruction is what type? Is it memory direct, memory indirect, register direct, register indirect? So it's kind of the immediate instruction where data is you are going to place in some of the memory location. So what is the type of addressing mode? Type of addressing mode. If you study computer organization, definitely you will learn addressing modes. There you will see the immediate instruction, or 1 byte instructions, 2 byte, 3 byte instructions. You will study different types of instructions, right? There you will see types of addressing modes. And type of addressing modes, if the machine supports, let's say, 16 addressing modes. For the 16 addressing modes, you require 4 bits, so that using 4 bits I can uniquely identify the 16 different addressing modes. So let's say my system is supporting 32 addressing modes, then you require 5 bits. So how many bits required, that depends on your system. Okay, let me say that 4 or 5. This might represent what is the addressing mode. A.M represent addressing mode. And then maybe you have operand 1, operand 2. Similarly, you require operand 1, let's say operand 1 something else operand 2. If you have any other, just include it. But this is how the assembler understands the whole assembly instruction, and it has a mappings inside, and it converts to the equivalent machine code. But whatever it does is already done by the compiler. It's just converting. Assembler is not having its own knowledge, right? It's just depending on the machine. But this is already done by the compiler. Take some address 1000 and I have the data 10, and it is the move instruction. The compiler already instructed the assembler to do this. So assembler is going to do by looking at its own mapping, because that mapping known to the assembler, because what system is actually having, that's known only to the assembler. If compiler knows that, then compiler has to be fixed to the system, right? We can't uninstall and install. So that's why we need the assembler support. Then after that, here what you have done is may not be available. Sometimes you want 1000 address here, but the 1000 may not be available in the main memory. Somebody might be occupied there. Then you require some support of loader. The loader comes into picture. It can alter the addresses of the instruction or data. So that is the next part. So whatever the address is produced, it's going to be relocatable, means it can be changed whatever the assembler does. It's not fixed everything here. What is fixed? The 10 is fixed, the operation is fixed, but this 1000, and it might be stored somewhere, right? Let's say 5000, because 5000 is an address where this instruction is stored, and that 5000 may be changed later. It could be moved to 6000 if the 5000 is already occupied. So loader decides. Here two things I'm talking about: this 1000, maybe that operand 1, and this address of an instruction. There are two addresses that you are dealing here, right? How many are dealing here? Two addresses. This is address of instruction, or you can say address of code. And what is this? This 1000, especially this 1000, is address of data. Address of data. And these two addresses are actually relocatable. So what assembler produces, it's not knowing about it. It will directly produce a machine code, but whatever the addresses it has, the loader understands it. Okay, some addresses which you are asking me right now, they are not available, so I will change them, but the logic will be same. There is no difference in the logic. You want to perform the 10 to be stored into the some memory location, it will do the same, but not exactly the address given by the compiler or assembler. Fine. This is about assembler. And really you want to know about assembler, okay, the whole thing can be done in one pass or two passes, right? To convert into the assembly to the machine code, the whole process can be done in either one pass or two passes. That depends on how the assembler is implemented. Fine. We are not going into that details, but anybody want to learn, yes, you can go for the assembler implementation and check that how the assembler does different process like compiler. Now we are almost near linker. As you know, the linker is going to help you when you are referring external references or external files or external variables. The linker main purpose is here. You have many things, right? Let's say this is your file, program file. This is, let's say, file 1. You have main function here. Let's say the main file for you, that is the first program need to be executed. There you have written the main function. But this is not only the file, right? There are many other files actually needed to refer. Let's say this is a file 2. You require to link this somehow. And there could be another file 3 you might require to link here, or there might be file 4, it might be linked to here. And how this is going to be resolved? Who is going to resolve? Is it preprocessor or linker? It's going to be resolved by the linker. But why do you want to refer external files? Because you might be using, or you might be calling the functions, or you might be using variables. What is this functions and variables? Sir, already I have the functions and variables inside the main. Why do I want the functions and variables from other files? Yes, you should. Very simple program that you are writing every time. Let's see that. What's actually happening? Ash include, let's say, stdio.h. Very famous, right? Then you write something here, void main. and then you write printf. Let's say this is the first program, let's say new. Now look at, is this one file? No, it's actually the file you want to execute, but this cannot be executed without stdio.h. That means there is another file which is linked here. Some file is linked which is stdio.h, and there is a corresponding library file where the printf definition already converted into a binary code, and this file, without this file linking, this file cannot execute. Then who is going to come into picture here? Right here, linker support is needed. First, preprocessor understand the statement, and it informs the compiler, don't look at this code. So linker is going to look at this code. Somehow the printf is going to be resolved by the linker by looking at this reference. By looking at this reference, stdio.h is linked to this file. So somehow the printf is going to look here. So the definition exists. It's going to be executed at runtime because it resolved. So linker helps us. It resolves all external references. All external references. What kind of references? Mainly files. But why do you want files? Because within the files you have the two things, either variables or functions. Sometimes you refer external variables, then also you need a linker. So this references depends, it's files actually, but it depends on variables and functions. Both are going to be resolved by the linker. You can try your own program. Basically, as a beginner, you always write a single program, but actually you can write many programs. You don't need to write stdio.h. You can write your own C program. You can include here, so that the linker is going to link that file, and during execution somehow it's going to be called, because of the linker helps to understand where the printf exists or where your own user defined function exists. Okay, so I will recommend to write many programs, many C programs, and keep the main only in the main program where you want to start execution of the program. So while you're executing this program, many files are going to be resolved or linked to this file to understand the code that you have written in this file. Okay, this is about the linker. Linker actually what does, even though you have different programs, it will make all the different programs flow as a single flow program, so that when the operating system starts executing, it looks like sequentially it is executing, like it's just executing like one program. It will not execute like a different programs, as the linker already resolved all the external references. Okay, so instead of printf, it goes to somewhere, because it might be providing the address here. It goes there and executes and come back. So it looks like simple function jump and coming back. Okay, it's about the linker. But I'm not talking about the linker, all the places that we use in reality in operating system. Okay, a linker might be used in various places, but I'm only talking about in C program how the linker is invoked. Okay, when it comes to implementation, you have again two types: static linker, dynamic linker. Static loader, dynamic loader. Okay, that you may learn in operating system or in some other subjects. Really not much required in today's modern compiler design for the GATE exam. Loader, again, the loader as a very big it's a very big topic in operating system, and we are not talking about all types of loaders, right? We are talking about how the C program takes the help of loader. Okay, here you have different files. It need to be loaded, right, to link. So linker and loader need to be communicated somehow, so that is it statically should be done or dynamically should be done is going to be implemented according to the requirement. So both linker and loader need to be communicated together, or need to be involved together to understand, do you want to implement static loader or dynamic loader? If the loader is static, then linker you can implement very simple, either statically or dynamically, because address already known, right? And suppose a linker want to be static, then loader has to be static. Why? Because linker is static means it need to resolve before execution. If you want resolve, you need addresses. If you want addresses, loader has to come into picture. So many relations are there. Okay. Now loader, what do you mean by loader here? I told you its main purpose in the conversion of C program high level to low level, it's going to alter, it alters or changes address of code or data whenever necessary. Address of code or address of data or data. This is called as relocation. What is this called as? Relocation. It means it performs, simply you can write the same line another way, it performs relocation. It does relocation. What is relocation? Nothing but altering the addresses of the code or data. That's why I told the instruction should be stored somewhere and the data should be stored in somewhere in the main memory. So for both of them you need memory locations. But what the compiler and assembler did is assume some address and converted, but that may not be available at runtime, right? The compiled code may be run, maybe you may run on the same day or maybe another day. Even on the same day, it may not be at the same time, right? You may run after a few seconds, but every second or every few seconds, the snapshot of the main memory could be changed because of you exit and start many programs, right? So that's why the loader and linker are really needed to compile and run the code. So this is about the loader, and it's about all components that we have seen within the language processing system, from how high level, from high level to low level, how the program is converted, and what are the components are involved. Preprocessor, compiler, assembler, linker, loader, all comes into picture. But all these things are just treated like a single program that you are not aware of it. Just you type or click on build and run button, it's going to happen all the things. Okay, you will only see how to enter an input and how to get an output. That's it. The whole logic is going to be executed because this translation done in background. Okay, now we'll move to the phases of a compiler. Phases of a compiler. I've already disclosed that how many phases are there. Let me show them in sequence. When you give a C program to the compiler, the first phase which comes into the picture is lexical phase, also called as lexical analysis. Then you have syntax. This phase is very important for the exam point of view. We spend a lot of time here than any other phase. Then you will have semantic analysis or semantic phase. These three phases are analysis phases. Then you have intermediate code generation. You can call it as ICG, intermediate code generation or generator. Then the output will be given to the code optimizer, or you can say code optimization. Code optimization. Then you will be having very important phase at the end. That's a code generator. This code generator is going to produce the assembly code at the end. Then after the producing assembly code, in case if you want to optimize the code, still you can apply this code optimization at assembly level. Then finally you will get the optimized assembly code. Now you can see the first three phases are actually analyzers. That is, they are going to analyze the program rather than converting into another form. The whole C code is analyzed lexically, syntactically, and semantically. Here, then the analyzed C code will be converted first time into intermediate code. Then you can further optimize that intermediate code to save your time and space. Then later you convert into assembly code with the help of code generator. So let me put all those conversions here. Here you give C code, and here it's important the analyze C code I can say, but rather than saying analyze C code, let me produce the uh, sequence of the conversions. Here token stream or sequence of tokens, token stream or sequence of tokens, the whole program will be converted into a tokens, sequence of tokens. Then here let me say parse tree, the whole program just it will be converted into simple parse tree, which will help verify the syntax. If there is no syntax error, it will produce the parse tree. Then semantic, what is a semantic? It's going to produce something like annotated parse tree, annotated parse tree. This annotated parse tree will have the semantics or translations or actions within that parse tree, which is decorated parse tree. And the intermediate code generator is going to produce in intermediate form. Here this intermediate form could be represented, I'm just saying intermediate code, but this intermediate code can be syntax tree or could be tree address code, could be SSA code, and could be directed acyclic graph. There are many intermediate code representations we'll be learning there. So by taking this intermediate code, we can further optimize, and you may reduce the number of lines, or you may reduce, or you may produce another intermediate code which can save your time or space. So this one is again intermediate code, but if possible it will produce optimized version of the intermediate code. If it is not possible, it will produce the same intermediate code, and this intermediate code will be converted into assembly code first time here, assembly code. And this assembly code, if possible, it will convert into the better version of the assembly code. This is how all the phases of the compiler are going to help us here. And let me help you the 6 phases. Okay, I'm going to use some short names because every time writing the whole name is difficult, right? The lexical analysis I will use, let's say LA, lexical analysis. Okay, syntax analysis I'll just write SYA, syntax analysis. Semantic analysis, let me write SEA, that's a semantic analysis. Then ICG, intermediate code generator, and code optimization, it's a CO, and it is code generator, and it's another CO. But these two different code optimizations, even though theoretically you will have the same similar concepts, but this code optimization takes intermediate code, produces intermediate code, but this code optimization takes assembly code and produces assembly code. That means both programs are different, even these two programs having the same name, code optimization, but code optimization on intermediate code, this code optimization on assembly code. Okay, so this phases I'm going to put into another way or another form, so that you will be having some other introduction to the phases of compilers. Okay, let me introduce that. How many phases we have now? 7, right? In the 7 phases of the compiler, the first one, the lexical analysis, then we have syntax analysis, and we have semantic analysis, intermediate code generation, code optimization, code generation, and finally intermediate code optimization on assembly code. Then what have lexical analysis to syntax, syntax to semantic, then semantic to intermediate code generator, to code optimization, and to code generator to code optimization, and final output. Clear? So now I wanted to point these things in different ways. That's why I'm going to write again. So here what do you have? Syntax analysis and semantic analysis, intermediate code generator or generation, code optimization, code generator, and code optimization. Sorry. Now there are right different phases. There are different phases we are going to use in two ways. Here, analyzers and synthesizers. What we call the first three are analyzers, but when you look at the whole compiler, whether it is analyzer or synthesizer, all of them are going to interact with one special data structure to understand the program. If you look at lexical analysis has to interact with the symbol table, and syntax analysis, and then semantic analysis, intermediate code generator, code optimization, and code optimization. All the phases are going to interact with the symbol table. We have the another one, which is error handler. This error might be produced at any stage or any phase of the compiler. All the phases are going to interact with the error handler. Lexical errors, syntax errors, semantic errors, intermediate, there might be fatal errors from other phases. Okay, mainly the compiler errors depends on the analyzers. Here, let me put into here. Here, it might be possible some kind of a lexical or token related errors. Okay. Here, you might have some syntax errors. You will report to the error handler, so that error handler takes the responsibility to produce the error to the user or programmer. And semantic analysis, some type checking related errors. So I'm just writing semantic errors. And other errors are basically fatal errors. They are unavoidable system errors, basically due to insufficient resources it could happen. Now, as I told, here there are few phases which are part of the analysis, other few phases are part of the synthesis. So which are the part of the analysis? The first three, the lexical, syntax, semantic, are going to analyze the code. So these three are called as analyzers. The remaining part is called as the synthesizers. Everybody is going to convert one form to other form. So these are the synthesizers. Among these four, the code optimization actually need not be, it's a separate phase. You can also implement is a part of the intermediate code generation. Here it's a part of the code generator, but to understand it's a very special in this compiler. That's why we need a different way to implement, so we can separate that too. The total 7 phases if you look at, and the first 3 phases are analyzers, remaining are synthesizers. Fine. Now what is symbol table? What is symbol table? We'll look into the symbol table once we complete all the phases, right? So we will focus on each phase. What is this lexical analysis, syntax, semantic, ICG, code optimization, code generator, and code optimization? Let me take some example to help you. That is, I take a very simple example to understand. Here, let me write here x is equal to a multiply b plus c. This is my high level code. And assembly code could be different, it might be possible that multiplication, let me write here, okay, r1 comma r2, and then addition, that r1 with, let's say, r3, could be some output. Just I'm saying it, it could be one of the possible output. If abc might be if they are stored in registers, this could be possible output, predictable from the compiler, because it need not be exactly, but similar one. uh, Now let's focus on the each phase of the compiler, how the each phase going to take an input and produce an output. Then we'll start one topic here. In the compiler, the first topic is lexical analysis. We'll spend a lot of time to understand how this is going to be scanned, but right now just see the input and output to learn. So as I told, it has a lot of meaning, like analyzers, synthesizers, and we'll see overall too. Okay, the first phase is lexical analysis, right? So what is lexical analysis here? Lexical phase, lexical analysis, phase analysis, both are same here. So you give input something like x is equal to a, what was it, multiply with b plus c. This is some high level C code. Now what is expected here? Expected something which is, don't worry what I write, but something like id1 is equal to id2 multiply with id3 plus c, like this. It converts everything into tokens. Maybe need not be x is equal to a star b plus c. You just give any other something like this. Temp is equal to some multiply with det something determinant plus, and I just want to say some other count. You could give anything like this also. It converts something like id1 is equal to id2 multiply with id3 plus, sorry, last one, not c, some id4. Need not be exact same subscripts, but similar to this. Now it produces, it collects, it groups the characters into tokens and produces the corresponding token. It may be id1 is equal to id1 multiply with id1 plus id1 if all are same variables. Okay. So this is the expected output from a lexical phase. Is it exactly the same way? Yes, it's exactly the similar way, but it's going to group. How it groups? Basically, it's a statement only, but first id1, that's for x, then equal to maybe some other token name, or it could be equal, next id2, next multiplication, next id3, next addition, next id4, next semicolon. So it's going to inform to the syntax analyzer who is the next token in this program. It's going to produce the sequence of tokens. That's what we call token stream. What we call token stream. This will be visible to the syntax analyzer. So now when syntax phase comes, it will be taken as an input. So what is the input of this one? Is a C code, right? High level code. What is the output of this one? Token sequence or token stream or sequence of tokens. This will be produced. And if it finds any token error, it will produce some error, or you can say it uses a symbol table. Somehow it produces error if there is any lexical error. What are the lexical errors? We will see in the lexical analysis. Okay, right now don't focus on what are the errors. Okay, this is about the first phase of the compiler. It simply does a scanning of the code and produces the token stream, and this token stream will be taken by the syntax analyzer. So what is the syntax analyzer job? The syntax analysis or syntax phase, it takes the program that you have, the token stream, the output of the lexical analyzer. id1 is equal to id2 multiply with id3 plus id4, and this will be taken and will produce a parse tree. Okay, what is a parse tree? That uses a context tree grammar to derive the string. Okay, don't worry much about it. I'll generate my own parse tree. Here. Don't worry how it is, because it might be my own compiler or my own context tree grammar. There will be root, and there is somehow to produce, there are variables, productions. Basically, you have a production something like inside s arrow a is equal to b semicolon, maybe you have here. Then this is a half of the parse tree, a part of the parse tree, and a will have something like id, and b will have something like c plus d. And what c does here, the id multiply with id, and d derives id. So this could be, one of the possible parse tree for the this string. It could be it's called as a now string. This is the string, which is actually the sequence of having sequence of tokens, and for this string you have the corresponding parse tree. In case if there is any syntax issue, this syntax phase will produce syntax error mentioning the reason. You see a lot of syntax errors, right, in the program when you have some syntax issues while you write the code. Okay, if you miss the semicolon, or if you don't write all the operands properly, you might get some syntax error that will be displayed by the compiler, in which line, which place possible syntax error exists. This is called as a parse tree. What is the output here? Parse tree. What is the input here? This is considered as a string here, but actually this string is nothing but token stream. Is output of the lexical analyzer, but it is input to the syntax space, and syntax space produces a parse tree, and this parse tree is input to the semantic analyzer. So okay, the same one, okay, I copy the same one to this semantic analysis. Here in the semantic analysis, the parse tree semantic phase or semantic analyzer. The input is a parse tree, output is annotated parse tree. Okay, there is some tree, right? S, okay, a is equal to b semicolon a to id, and I said c multiply, sorry, addition d, and c has some id star id d to id, possibly same. Yeah, perfect. Now this is the input to the semantic phase. Now what is the output? Okay, it looks weird as you are not aware of the compiler if you are beginner, but still you should look at this is a parse tree, and what we are going to produce here, annotated parse tree, that we are going to decorate with some translations. I might have some meaning inside. So what I do here, I produce the same code here, that same thing I produce here, equal to b, and I might have some rules here inside. Don't worry what are those rules, but here there is a meaning here. I'll write something here to check the types, is that a and b are having the same types. If a dot type is equal b dot type, there is no syntax error. In case if you see here, if a dot type is not same as b dot type, it will produce a semantic error, because its expression, this type should match. Okay, if it is not going to support implicit conversions, directly it will produce an error. Okay, id, and it will assign somehow this id dot type to a dot type, and b gets the types from the c and d, but c gets the type from id multiplication with id. These two types are matched, then c dot type is same, and d dot type is same as id dot type, and c dot type, d dot type, if they are same, then b will get the same type. In case if it any mismatch at any subtree, then it will produce the semantic error. So here each place it's going to check the types. Even here also there is a type checking. Okay, I'm just putting the dots, but assume that they are the annotations here. They are going to have some translations. Now id multiplication with id, it, the translation no need to be at the end. It depends on what kind of translation you need it. And d id, and that type will be decided here. id dot type will be assigned to d dot type. Okay, so all the things are actually done by the SDTs, are going to help us to do this semantic analysis. So we are going to use syntax directed translations, which are going to help us to perform the semantic analysis. Okay, you will be writing something like s arrow a is equal b semicolon. You'll be writing the production like this along with some translation. Similarly, you are going to have the grammar. Actually, your grammar might be used simply a is equal b semicolon, but there is a translation added to that context free grammar, so that we call it as syntax directed translation. Here when you look at the grammar, your grammar might be looking like this. B is equal to C plus D, and C derives ID star ID, D derives ID. But here the translations are added. This is the context free grammar, but here the context free grammar along with the translations called as syntax directed translations. That syntax are actually directed to the some meaning, so we call SDT, syntax directed translations. Fine, this is about this semantic analysis. Now this one, once lexically, syntactically, semantically correct, then this code will be converted into the intermediate code. So intermediate code generator is going to help us. Now when you look at this code, the intermediate code generator or generation ICG, what it is going to do here, no doubt the analyzed code comes here. That analyzed code, what was that analyzed code here? Something like, right, x is equal to a multiply b plus c. After verifying lexically, syntactically, semantically, that code is taken by ICG and it produces some form of intermediate code. There are many forms for intermediate code, like syntax tree, directed acyclic graph, tree address code, and control flow graph. There are many things. I'll take one of the best form. This is high level code. I'm just saying analyzed high level code, and now it produces the intermediate code. What is this intermediate code? It's something like P1 is equal to a star b. Using that annotated parse, it knows now the SDTs. Using SDT only, it can produce now that a multiply with b should be stored in some temporary variable or some variable which is right now has no use, and the t1 plus c might be stored in t2, and that t2 might be moved to x. It produces set of some 3 address intermediate code, and this output is example I have taken here is 3 address code. 3 address code is also called as 3AC, or you can say TAC. Okay, I've just taken one example here. Okay, but no need to be this 3 address code. You can also draw a syntax tree here. You can also do some other graphs here, control flow graph, something like that. Now this code can be further optimized. How? See, instead of storing in T1, if really A is not used in the future, you can also store the result in A, or you can also store the result in B if A and B are not used after multiplication of A and B. Then you can reuse the variables. That is done by optimizer, code optimizer. So I'll take this code. T1 is equal to A multiply with B, and T2 is equal to T1 plus C, and X is equal to T2. These 3 lines I'll take. Code optimization I have not taken here, but let me help you here itself because I have taken a separate topic. In case if you want to optimize further, yes, this can be optimized. This may be optimized further, right? So I'm just dealing this as at the end, but assume in case if you want to optimize, then how do you write? Something like A is equal to A multiply with B, and then this A plus C Again, you may store in A in case A is not useful in the future, and that would be fine. X is now A. In future that A is not there, then wherever you want X, that place you can use A. See, just A, B, C. 3 variables are not enough, but here you require 4 addresses. So you are saving the space, and here 3 instructions, here 2 instructions. See, the space is saved and the calculations are also here. This is additional cost you needed moving. Here you don't have extra move. So that's optimized version of the 3 address code, optimized version. So in case if you want to optimize further, so you may be considered this one, optimized version. Okay, that will take care of that will be taken care by the code optimizer. Now the code generation, when the code generation says you got a 3 address code as an input, code generator or code generation. Okay, what it does, it takes the input as some intermediate code, right? Some intermediate code. So one example I have taken as 3 address code, which is having something like A is equal to A multiply with B, and then that result will be added with the C and stored in A. This is one of the possible 3 address code. Now correspondingly, it will produce, I told in the beginning that it may produce something multiplication like R1 comma R2, this corresponding multiplication, and then here addition, what is that, R1, the result, right? R1 with some R3, the C might be in R3, it's a corresponding result. This is a possible assembly code. In case if it is possible to optimize, it will, otherwise it will produce the same assembly code. So this is assembly code, right? So to do this, every 3 address code instruction or every intermediate code instruction need to be understood by the code generator. Okay, here the multiplication is there, that's why it's producing mul instruction. Here addition is there, so it's add. In case you require extra assignment, you require a move here. So it's all understood by the code generator. Okay, now code optimization, that's why I told this can be used in 2 places, code optimization on intermediate code optimization on assembly code. So that can be dealt with a lot of different code optimization techniques, and that we will see at the end. But there are 2 kinds of code optimizations, right? One, you have the intermediate code level. This intermediate code will be given to code optimizer, and it will produce again intermediate code. If possible, it will optimize, right? Another kind of code optimizer is an assembly code, but both code optimizations are different and executed at different places. This will take assembly code. If possible, it will produce optimized assembly code. The output is also again assembly code. Fine. This is about code optimization. That will be the last chapter for us, and in the last lecture we will be dealing, we are going to deal the different optimization techniques at high level, at intermediate level, and at a low level. So we are going to see all. Okay, now we have seen we have 7 phases in the compiler, and all the phases are going to interact with the symbol table. Now what is the symbol table? Basically it is a data structure. What is it? It is a data structure only. Table, right? It is a data structure. It's table. Okay, of course table may not look like exactly the same. It depends on the compiler how it was designed, like using array or using array of pointers. It might be mixed of many things. Okay, when you write a program, basically like int, temp, something like that, int can be understood by the compiler. It's int understood by the compiler, but temp also understood by the compiler. But temp is the name given by you, right? Int is not given by you. Int is a reserved word, so that compiler knows it. Int means, okay, int is going to mention temp is going to hold an integer with the size either 2 or 4 bytes. So type and size are decided by the compiler by looking at the int. But temp is the name, right? Name, you might be giving x or temp or count. You can change the name as you want. But program, in the program you might be using many places this temp, right? So compiler is going to analyze this temp and how many lines it has occurred and how you are using it, how long it will be useful. In the future you might be needed to optimize this variable further. So it's going to maintain, right? The temp is going to store in the symbol table somehow. It's going to store in the symbol table. The temp is actually lexim. Internally it will give a different name, let's say id 1, and it's going to maintain what line it is, maybe let's say line 10, or in future you might be getting different lines, but assume that if line maintained that line 10, let's say that number 10, it might be the instruction. This may be avoided. Maybe in future it might be using offset. This temp variable created at some offset from the function, because function also stored at particular location, and from that location of for this temp is declared, or temp is assigned to the particular memory location. Let's say x some location, some offset it is, and so on. There are many things to optimize further. And what is symbol table basically? It's a data structure. It's going to store the attribute information of the token. So if there is a particular token, right, or identifier, you can say this is identifier. Even for the function name also you might have an entry here. So it's basically the symbol table stores all required, all attribute information. Attribute basically we say columns, right? So every column has the different name that we call as attribute. All attributes information of an identifier, of each identifier, let's say, in the program. This is the main purpose you require. This is the main purpose you require, so that the lexical analysis, it will store the token. In syntax analysis maybe line number. In semantic analysis maybe type, what type it is, let's say integer. In intermediate code generation maybe offset. In code generation maybe address or register location, that's exactly where do you assign it. Many things, right? Every phase you require. Like in code optimizer, maybe this temp could be replaced with some other variable or other addresses. So it's going to be maintained in the symbol table. Okay, the symbol table is going to help to analyze the code in various phases. It's the main purpose of the symbol table. In the previous gate exams, it was asked like what data structure is used in compiler. They have given one of the options, symbol table. So what is a symbol table? Right, it is a data structure that stores all attribute information of identifier. Okay, now before going to the next topic, right, the first topic, lexical analysis, let me tell you errors, because you have error handlers, right? In the errors we have the lot of errors. It means at every stage you may get a different kind of error. One kind of error is a preprocessor error. Preprocessor can also produce errors. When it produces, you have written hash, you have written something like include, and you have given spaces much, or you have written something like stdio.h. See, it's not actual, right? Actual it's not a command. If it is preprocessor command, here should be 1, here less than symbol, here greater than symbol. You have written here 2 less than symbols. Here preprocessor will produce an error. It's not the preprocessor right command. Actually, hash tells the compiler that it is your command. When the preprocessor trying to analyze, it shows that there is something wrong with this command. So you have to verify what mistake it is. So even include the spaces many here, it will produce the preprocessor error. Other errors are some compiler errors specific to compiler phases. They are maybe lexical errors. We'll see in the lexical analysis. Maybe syntax errors. We'll see in syntax analysis. There could be semantic type related errors, type mismatch errors, main compiler errors. Some errors are runtime errors. During execution, you may face a runtime errors like divide by zero error, or you are accessing an element which is outside the array declaration, like you declared as a of 10, but when you declare a of 10, 0 to 9 only accessible, but you're trying to access out of bound, then you may face runtime error. Or you are dealing with the pointers and you are trying to deal with the wrong addresses, then you may see the runtime errors. Okay, there are many runtime errors. Definitely, we're going to see them at the end. Now, with this, we have understood just what is a compiler, what is there inside the compiler, and how many phases are there in the compiler, and how they are going to interact with the symbol table and error handler to do the compilation process. And now the first phase of the compiler is the lexical analyzer, right? So let's begin the lexical analyzer. We have already know what is lexical analysis. What is lexical analysis? Lexical analysis. What is the lexical analysis? It takes the C code or high level code and it produces the sequence of tokens, token stream, basically sequence of tokens, also called as token stream, or simply just a string token stream. Just it looks like a string, whole program converted into one small string, right, by introducing the tokens. If there is any error by this, it will produce lexical error. It will report to the error handler, and error handler may handle the errors, or it will report to the programmer these are the errors happened. So you give the facility to the error handler. Really you wanted to correct the errors through the program. You can also do certain errors handling with the help of error handling program. And also you have a symbol table. Whenever you detect or whenever you see any identifier which is first time appeared, then you can put in the symbol table. Later on you refer it whenever needed. Okay. Now this is the main part of the lexical phase. What it does, right? It the first thing is, when it sees the C code, it's going to group the characters and converts into token. Like whenever it sees MAIN, the 4 characters, right, it's going to group. Like it starts somehow, it groups M, then A, then I, then N. Okay, it knows somehow using with the help of finite element or regular expression, with the help of patterns, the main is one token which is identifier type. So ID1 might be generated for the main because it's not a keyword, it's an identifier. So maybe ID1 is the corresponding token name for the main. So this will be produced by the lexical analyzer. So it's going to group the characters into a token. So the job of lexical analyzer is it scans whole program without leaving any character. It scans all program. Remember, it scans all program. It can't ignore even single character. Of course, to generate it may ignore, but to scan it will not. It has to reach every character of the file, from first character to last character, without ignoring. It scans all program, and what it does, it converts, right? It is going to group the characters into token. It groups character sequence. It groups a character sequence, one or more character sequence, into token or tokens. whenever it detects some a meaningful character sequence, it produces a token. So it's going to do every time it finds a character sequence and produces a token. So every time it's going to do the job till the end of the program. Example, if you write this program main something like this, int and so on, if you are writing this, it detects this one, then it detects the open and then closed and then open and then int. It's going to group the characters and identifies the tokens and produces. So when it does it, it's just 1 2 3 4 5. It produces corresponding 5 tokens in a sequence. You don't need a spaces, because the spaces are only for identifying the tokens here. The spaces are basically required here to separate the tokens. Apart from that, you don't need spaces here at all. Okay, it groups the character sequence into token. So it produces a sequence of tokens by scanning whole program. It converts whole program into token stream. It converts whole program into just one token stream. It's simply a string, looks like. Okay, but how this is going to convert? It needs to group the characters, right? How it's going to group the character sequence? There is a rule. Suppose you have something like MAIN, right? But M is a valid token, even A is a valid token, I is a valid token, N is a valid token. But it's not going to detect 4 tokens here. It knows that it is a 1 token. How? It's going to start here. It's going to follow maximal munch rule. It's going to follow longest prefix rule. It's trying to detect what is the longest prefix. M valid, MA valid, even including I. MAI is valid, MAIN is valid. So it's going to group M, MAIN. So each character is going to group with the previous group. Then it's going to find which is the longest prefix. When you have the here open parenthesis, then it knows that open parenthesis cannot be part of the identifier. So it detects the longest one till here. So this is called as longest prefix match. It's called as maximal munch rule. So it's going to use to detect the token or to group the characters into a valid token. It uses the rule. It uses what rule? Longest prefix match, or longest prefix rule. Simply longest prefix match, or you can also call maximal munch rule. It uses a longest prefix match rule to produce or to identify tokens. While scanning, this is a very important point. Each time it detects a token, it will start again grouping the characters with the help of the syntax analyzer. It always communicates with the syntax analyzer to do this thing, to detect or to separate the tokens. If you get the space, then lexical analysis job is so easy. If you don't get the space, then it has to separate the token here, but that cannot do alone. So it takes a little bit help from the syntax analyzer. Okay, anyhow, if you want to think about lexical analyzer separately, these are the main points which are needed. And during the scanning, many things are going to happen. What are the other things are going to happen? Like spaces here will be ignored by lexical analyzer intentionally, because they are no meaning later on. They are having no meaning later on. So spaces that you see, white spaces, right? When you write here main, you have lot of spaces, and these spaces you see here, right? Lot of spaces, they are ignored. They are intentionally ignored by the lexical analyzer, because already it's a token separated. This token separated from here. So here what it produces, like T1 for this T2 for this T3, and to specify T1, T2, T3, you don't need spaces, because T1 means main, T2 means open, T3 means closed parenthesis. So these spaces are only to identify the tokens basically. If even though you don't have the spaces, the lexical analyzer does that, identifying the tokens. Now what I told here, it's going to use the longest prefix match rule to produce the tokens. While scanning the whole program, I have just discussed, it ignores few things. It identifies basically not only tokens, it also identifies comments, white spaces and white spaces and spaces, and the job of lexical analyzer to ignore them. It identifies, then it ignores them. It is also the job of the lexical analyzer. And when you look at the lexical analyzer, you need to understand these points. Also, when every time the identifier appears newly, it's going to store in the symbol table. So it is also having another responsibility. It stores the identifiers in the symbol table whenever they occur first time. So let me write somewhere here at this point. It stores, or it creates the symbol table, because the first time the symbol table is needed here. It stores identifier. What information needed here? Basically token information. It stores identifier or token information. You can also say it stores token information in symbol table whenever you see the identifier. Fine, these are the things needed for the lexical analysis, right? Now you might raise one question, sir, you also explained about lexical error. Who is going to produce a lexical error? Lexical phase. So if you want to understand them, whenever you are trying to group the character sequence into token, if not possible to group, then what happens? Immediately it produces. It is also responsible. It produces lexical error if invalid character appears in a sequence. Invalid character seen. Invalid character or characters. If invalid character sequence appears, it is not able to group into token, it means there is something wrong with the program. You have not written a valid tokens. When will it happen? We have to see in this lexical analysis. With this, almost all theoretical points are covered. Now your job is how to perform the lexical analysis. You got all theoretical points. Now let's look at this examples. Before the examples, if you want to relate with the theoretical theory of computation or automata theory, to perform this lexical analysis, you may use either a regular expression or finite automata. If you want to design this, you may use either a regular expression. This is a very special topic, or you can use a finite automata. Can be used to design this. Can be used to design lexical analysis theoretically. Okay, let's start with this lexical analysis. Let me start with a few examples. Now I told you need tokens, right? Always important. What is token? Token, and also there is a word called as lexeme. Basically lexeme is what you write in actual logic or actual program. Suppose I am writing a program like main, right? Okay, it's not always like this, just for understanding these words. Otherwise you don't need the difference between token and lexeme. Do you think they are different? No, not at all. For the programmer both are same. Only the for compiler side, because as a compiler sees as the a different. That's why I'm talking about compiler side, not your side. Programmer, there is no difference. Token and lexeme, they are same actually. But for the compiler side, what happens? The lexeme means what you are writing here. The main, these are the lexemes basically, main and open parenthesis, closed parenthesis, then bracket, this int. These are actually lexemes. It's going to do like this, lexemes. It's trying to treat different lexemes here, but each lexeme we might write a different token inside the compiler. Once it sees the main, it does something. It will relate some other way, like id1. This main might be id1, and this might be, if it is operator, it could be having some different name here. If there are many open parentheses are coming, maybe it will give some name like open parenthesis 1 or op1, something like that. And this one, the first one coming, let's say closed one, or if it is another, this open brace is coming here. Int is a keyword, so it might mention like int might be, let's say a compiler has already mappings for each keyword. Let's say int might be k1 or k10, k100, whatever it is. Maximum 32 keywords, right? So give some subscription between subscript subscript in between 1 to 32. And x is identifier, not appeared at, so it might be the first identifier, but already one identifier appeared as a function name. This is a variable name, so id2, but first variable but second identifier. And semicolon is a very punctuate special, right? So I might have, let's say p1 means punctuation symbol, and this one is the first one, so I can keep like this. It's your choice, it's a compiler choice whether these two are same or different. Is that clear? Sometimes you may see same, sometimes you may have a different mappings. That's fine. The lexeme what you write, token what compiler analyzes or understands. Okay, compiler sees this one and might be storing this one, but still the each token uniquely identifies the lexeme, right? For this you might have the table for them, like constants it might maintain literal table, and for identifiers it may maintain the symbol table, and others already compiler has. Int already has internally the meaning for the int, so int might be int only if you do, if it do not want to replace with any other. So int also is the right word to put in the token. Okay, so this is what the difference. Lexeme what you write, token what is understood by the compiler. But lexeme is nothing but group of characters only. Token is also group of characters but replaced with some token name. Okay, so each token uniquely represents the lexeme here. Whenever I say id2, it's x. Whenever I say k1, it's int. Whenever I say id1, it's the main. So it uniquely represents a lexeme of the program. This is the difference between lexeme and token. As I told, we are going to begin the types of tokens. When you are doing this many things, how many types of tokens are there? How many types of tokens? Do you have any idea of this? 5, 6. Okay, depends on how you analyze, but I just converted all of them into 5. But some books they say 4, some books they say 6. It's fine. Okay, how many types of tokens are there? Here I'm just saying the 5. They are keywords. What else you have? If you look at here, keywords, and what else you have? Sometimes you have identifiers, that main, x. What are they? Identifiers, whether it's variable name or function name or structure tag, they are all identifiers. What else you have? Sometimes you will have operators like equal, plus, minus. So they are operators. Sometimes you may write constants, maybe integer or character, string. So you might have literals or constants here. And apart from this, special symbols you may call special or punctuations. Okay, so constants, and finally you will be having punctuations or special symbols, let me call as a special symbols, including punctuations. I have divided all of them into just 5 types of tokens. You just remember them, these 5 types. The whole program actually, the sequence of tokens, and every time you detect the token, that should be belong to one of them. If not, then it will produce lexical error. If not, it will produce lexical error. Okay, I hope you have clarity of the tokens now. I am going to start with examples, but each time I analyze the example, I do with a different example, so you need to practice. In case if you are not aware of the tokens like keywords, what are the keywords, what are the operators, you must learn before practicing this example. I believe that you are good at C program. In case if you are not learned C program, so it's better to learn a little bit of you should have little bit of programming knowledge before analyzing this, so that you will know how compiler works. Okay. First example. It's a very simple one, just to find do you have any lexical error? If no lexical error, how many tokens are there? Is it clear? Do you have any lexical error? For that only you should know, for that to find do you have any lexical error, first you should analyze, is it producing any lexical error? Check. In the beginning, so I may not give lexical error. So it does like this, it starts scanning here and it does first character, second, third, fourth. Now you got a space, so it detected as one token. So I'm just writing the corresponding the token here. Okay, first token, let's say T1. Don't worry what is T1. Okay, that void is a keyword, maybe it is a K1, but I just want to say T1, T2, T3, that's all to maintain the count. And then space, what happens to the space? Space is ignored, it will not be counted as a token, but it is identified by the lexical analyzer. It is identified, so it is ignored. Then it starts scanning from here, MAIN. Then after that, open parenthesis, the different token belongs to, it is not the part of the identifier, and somehow it has a rule, identifier rule, so it knows that main is another token which is identifier, which is T2, let's say. Okay, the T2, so T1, T2, I'm just writing this is T1, T2, and then open parenthesis, then space. Without space also it does, it's as a separate token which is T3. Then if you have the space, fine. If even though you don't have the space, it will detect as T4. So now T2, T3, T4. See, when I am producing, I don't care the space, I don't have the spaces at all. Now T5 is, I'm going to write immediately after T4, because the spaces are only to understand how to group the tokens only, right? Once you have the tokens with you, you don't need the spaces. In fact, later we also delete the semicolons. In fact, we also delete the declarations, because compiler going to learn a lot from this code. Okay, when you convert this code into the machine code, you don't have anything here, it's mapped. This index also, it's not there. X is the 2 bytes or 4 bytes, it's going to remember the X mapping somehow. So it's something different when you see the machine code. You can't see everything in terms of lines only. This line may not have the line there, it might have the layout and stores this information somewhere. Okay, some statements you will see the conversion, some statements the compiler does the mapping into some layouts or some other files, data files. Okay, now this one is the next one, right? This one will be T5. Okay, T5 here, and then a space, white spaces ignored, and then this one is a T6. See, this is going to be your the token string or token stream. Then space, this int is the keyword, X is identifier, this is a T7, and next semicolon, that's a T8, token 8. Okay, some tokens might be same, like semicolon might be appeared many times, so you may give a different token name or same, but total how many tokens? Total so far 8, and the last one is 9, T9. Total 9 tokens. Some tokens might be repeated, that's fine, we don't care, but total tokens recognized 9. So I can say here no lexical error, as I am able to detect the token for every group that I have formed, no lexical error. And how many tokens we have here? Total 9 tokens. Sometimes it could be possible, how many times identifier appeared while scanning? Main, one identifier, X another identifier 2 times. Okay, how many times? 2 times. How many keywords appeared while scanning? Void int. So some interesting questions might be asked, you should be ready for them. So this is the token sequence or token stream, or simply a string that will be given to syntax analysis. Okay, this will be the input to the syntax analysis. May not be exactly this way, but I told, it's a compiler decision how it's going to convert. Maybe this one, or maybe some other one, like the first one is a void, maybe keyword, right? So k1, and next one is the main, maybe like id1. Next, open parenthesis as it is, close parenthesis, and the open bracket. Then int is another keyword, let's say k2, and id, that's the second id, id2, semicolon, maybe semicolon, maybe closed. This could be the another possible the token sequence. That's fine. How the compiler does its own job, right? Fine. This is how the sequence of tokens produced by the lexical analyzer. The better way is to understand this one. It's generalized and everybody can understand. But this thing is, sometimes I keep the same, sometimes I convert into some other labels. That's okay. But this is the best practice to do. Fine. And now this is the first example, right? Let's go to the second example. Int 1, 2, 3, semicolon. Of course, you may have a compiler error, but lexical analysis may not identify sometimes. Other phases may identify. When it comes to lexical analyzer, yes, the lexical analyzer will not have power to recognize the error, compiler error here. Why? When it is trying to group, it looks like everything is fine. You see, int one group, let's say t1, token 1, keyword 1, space ignored, 1, 2, 3, it's t2, and semicolon t3. The corresponding output will be t1, t2, t3. That's it. But when you look at the syntax or meaning, you see that the 1, 2, 3 never be identifier name, because int there should be variable name, and variable name never be constant, never start with the digit. It's already started with the digit. So syntax is not appropriate. There is definitely syntax error, but not lexical error here. So here I am saying no lexical error, and definitely which error you will be having? Syntax error exists. It means somehow compiler error is there. Compiler error means it may be lexical error sometimes, maybe syntax error, or maybe semantic error. So anyhow, the compiler error is there somewhere. Okay. If they ask about compilation error, yes, there is a compilation error without any doubt. That is not happened in the lexical, but it happened in some other phase, later phases. Now, how many tokens we have? 3 tokens recognized in the program. How many tokens? Find the number of tokens in the following program. Then if this program is given, you should produce, or you should say 3 tokens. Don't worry about duplicates, like x is appear 100 times, but 100 times it has to understand that token, right? So when they ask find the number of tokens, count every token which is appeared while scanning. Okay, but compiler understands different way if the same token appears again and again, but it has to recognize somehow. Okay, by looking at the symbol table, or it has to implement internally. Let's move to the next one. Do you have lexical error here? No lexical error. Do not say lexical error, as it is a syntax error, because after int it is expecting identifier. There is no production, or there is no syntax rule in the compiler to write this line int space a constant, right? The 1, 2, 3, and this is very difficult. Actually, it's not the proper code in syntax. Third one. Now, Okay. Now int, great, token 1, what happens? 1. Previously 1, 2, 3. What is it? 1, 2, 3. It's actually what? Integer constant. Integer constant. But what is 1AB? What is this 1AB? When it started with 1, it predicting the constant might be coming. But after 1A came, then immediately it will produce error, because invalid sequence happen, then lexical error will happen. Because the A cannot be part of the constant, and it's predicting constant now because you started with 1, and identifier name never be starting with 1. But I'm not worried about is it identifier or constant. I only know that 1 started, then it should be a constant. That's all lexical analysis does. It doesn't know you have something before, after me. It never looks at, because it's not going to worried about syntax. It's only worried about what I'm grouping. Am I grouping something which is meaningful? I started with 1 means I should see only the constant, because there is no one will begin with a digit except the constant, integer or real constant, something like that, right? So here 1 started, that means in compiler the implementation after 1 it only looks for the digits or decimal point, something like that. But this thing 1 followed by A has no meaning to the group. So immediately what happens, it's trying to produce T1 followed by something, but here there is a sequence, invalid sequence happened, invalid character sequence, immediately produces the lexical error. Once you have a lexical error, please don't find how many tokens, as already we have done mistake here. So once we have a lexical error, maybe it will cause a lot of syntax errors. That's the reason first you keep valid tokens or valid lexemes, then write the syntax properly, then check for the proper semantic, then your program may be logically correct. Still we cannot guarantee lexically, syntactically, semantically correct. Still you may have the logical errors. So how many things you should take care, right? See, when you are writing a program, first ensure your program lexically valid, then syntax check properly, then semantic, all the types have you done properly, like expression, left, LHS, RHS, and parameters that you pass and that you take and that you return, everything is proper. Then logically also it might go wrong, even all of them is correct. So at compilation time we'll check this first 3, and during runtime you will get to know your logic is wrong. Clear? But you should follow a sequence, always follow this sequence, must ensure all the tokens you have written properly. That means you should write the token simply. If you write invalid token, then you will have syntax, semantic, everything is possible. So ensure lexically valid, then ensure syntax is correct, then ensure semantic is correct. Then at runtime you will get to know whether your logic is right or wrong. Okay, you will focus on logics, but the system will not understand your code unless you follow the compiler rules or language rules. Fine, this is the lexical error, right? Third one is lexical error. Let's go to the fourth one. The fourth one, int, same, 1 space A, B, and then semicolon. Now what happened? When it is trying to group, it groups now. Int is token 1, 1 is 1 space. I told you space is going to separate the tokens at any cost. So 1, it's constant. Now AB, it looks identifier, semicolon is special symbol, punctuation. So now it's going to be 4 tokens, no lexical error. But there is a compilation error. What compilation error? Syntax. Why? After int you are writing 1 actually represent what? A constant there. So this is not going to be appeared just after integer keyword or float keyword. So already the grammar has the rules. This one should never come there. 1 is not going to come there. So here the syntax error present, but not lexical error. Previously you have seen when you write 1AB, error, When you write 1, 2, 3, no error. When you write 1 space AB, no error. Because just going to look at what I'm doing, not who is there before and after. That's what the lexical job, right? So this is going to be no error because of the space. It's going to assume two different tokens, but there is here syntax error but not lexical error. But what do you have? But syntax error exists. Why syntax error? You should go a compiler and check the grammar, and after int can you produce a number or a constant? Not possible. That's why it's going to always, you have seen, right, int x, int temp, you need some variable name there, identifier there. Clear this point? Fifth example. Now sometimes you write the comments, right, int x semicolon, you write some comments here. Okay, what happens now? I told you that the comments are identified by the lexical analyzer and also ignored because it's not going to be considered as a token. What it does is it's going to be producing token 1 for this, token 2 as an identifier, token 3 as a punctuation, and this thing, whatever you see here, how it's going to be identified, this comment is going to be identified with the pattern. You see this pattern, right, slash star. It's called as a begin. It will not look for end at all without have a begin. This is very, very important. It's begin occurred, then only it will look for end. If directly end happens without begin, it will not consider as a comment. It assumes, like, you are writing multiplication or division, some operators you might be writing. So it's not going to understand this. It's not a pattern at all, right? Without a begin end, it will not understand because the pattern will have the begin and end rules. Now this begin and then it has to end somewhere with a star and slash. This is what end rule. In between, doesn't matter what you write. Before star slash, if you don't have star slash here anywhere, that will simply assume comments, right? Even you write one more star slash, doesn't matter. It just considered as a part of the comment because this is already begin happen. It will only look for end now. If you give again begin, it will not care. It will only care where is the end. So remember what is happening, begin and then only look for end. If begin not happens, then it will never look for end. So begin is the very, very important sequence. Now it's a begin happened here. That is the only reason it's looking for end. If this is not going to happen, it will not look. It will start here. Okay, comments, identifier, in identifier, program identifier, star operator, slash operator. It will do some way, right? So be careful here. This is happened. So it's a begin rule of the comment. So it's look for end. Here end rule for the comment. So whole thing is ignored, simply ignored or deleted from the program because the valid comment. So it's identified with this rule. That is the reason it's ignored. And later, whatever is after is another token, T4, T5, T6. So how many tokens it is produced? It's produced something like T1, T2, T3, T4, T5, T6. Total 6 tokens scanned in the program. Among them, 2 keywords, 2 identifiers, because keywords identifiers are the easy way to recognize rather than operators and other special symbols. Okay, and constants are also easy. So keywords, identifiers, constants are pretty easy than operators and punctuations. Why they are not easy? Because sometimes you don't understand the operator or punctuation. Okay, like if I say open parenthesis, close parenthesis, that comes under parenthesis, and really difficult to understand, is it one token or two tokens. That's why some things better not to discuss about them here. Okay, this is about the fifth one. Now let's move to the another example. Do you have any error here? No error at all. No error at all, right? There's no error in this program. It's compilation successful, will be successful, no doubt. The sixth one. When I'm writing something like in the program, don't worry, main I have not written, but still understand, x is equal to, somebody written y plus plus semicolon. Don't try to understand the meanings also. Don't say that x is not declared, y is not declared. We don't care now. Who is going to care that? If you have written this code within the main, who is going to care that x is not declared, y is not declared? The semantic analysis. The syntax is correct, lexical is correct, but semantically x and y don't have the types, because symbol table it is going to look at, it's going to trying to store the types, but you don't have the types. So it's going to generate the semantic error. This one is lexically correct, syntax is correct, but semantic is wrong. Okay, so semantic analysis produces error where the type mismatch happened to LHS and L value and R value. Okay, fine. What happens now? How many tokens we have? The first one, x token 1 equal operator, y is the identifier. Now double plus is one token or two tokens? I told you the longest prefix rule, right? It starts from here, it will take first place, it's token, but you can't decide now because you need to scan further. Longest and double plus is also one operator, yes or no? Even it may be two character, double character operator, but it is single operator, right? You can't assume it is two operators. It is a one increment operator. It's when you look at here, it's a post increment operator, not operators. Okay, so one operator, so it's a one token here. So this one is considered as one token, which is T4, and increment operator, that too, it's a one token. Total, you will be seeing 5 tokens in a sequence. The total 5 tokens, right? You should know how to do that longest prefix match. I'll give some instances like left shift, after that you see equal. It's just one token. Why? Because when you see the assignment along with other additional operators, this is going to perform something like that, right? X left shift equal to y is nothing but x is equal to x left shift y. The meaning of this line, right? So this is going to be considered as one token. Not only this, when you see double equal, or when you see not equal, or when you see left shift after that equal is there, again this group 3 characters is the single token, right? It's a single operator also. What else you have? Like logical and logical or, looks like there are 2 characters, but don't assume 2 tokens, they are single tokens. Okay, what else? If you have seen many things, and you may do some mistakes here, let me introduce that too. 7th example. Int, very interesting example, star star triple pointer, we say that. How you do it here? Int is one token, fine. That star, people might assume it is the one token. Wrong. It's not one token. It is not one token. Why? You might be saying triple pointer, doesn't mean that it is a single operator. The triple star, if you look at your operator presence table, when triple star comes, it follows right to left, and the first star is going to be having highest precedence. This star is one operator. It is dereference operator, and that is used 3 times. when you have this triple star P, what happens? It's going to be assigned like this. It's going to understand this way, right? The star P, and again a dereference on that, again dereference on that. So it's going to understand that way that when you declare this is a declaration, right? You are not also accessing some particular layout, but what is it? It's actually when you write something this, the P is a variable. What is it? P is a variable. Which variable? Pointer variable. P is a variable, and that's going to point integer, that's going to pointer to integer pointer. So 3 pointers are there here. So P is actually a variable. The other 3 stars are going to tell that how many levels you need to reference or dereference, you can say. So now here what happens, that's what I said, the we do some mistakes. One of the mistake might happen here. Actually it should be like T2, this one is T3, and this one is T4, and this one is T5 and T6. So total you have here 6 tokens and no lexical error, no lexical error. And next example, 8th one. Sometimes we may write in and keep some comment here. Very famous example, star slash, and you write without any space here T and X. After int you write a comment, it will work. What you however you may predict as per your understanding it works properly, but here your prediction may go wrong. Why? You might be assuming int is a 1 token. No, int is not going to be a 1 token here. This in is actually 1 token, and this is ignored by lexical analyzer, and T is another token. It is not going to have a much memory to remember all these 3. Whenever something is recognized, you got something to detect. Now I want to start another rule, then previous one is separated. It can't remember this one. So it will throw is the token and will start identifying the comment. Once it is over, then it will ignore, it will start another token. Once it is over, it will start another token, like this. So do not assume that you can include the comment anywhere, but not like this within the in between the keyword. So don't do that. It's going to separate the keyword. Now this 2 will act as 2 different identifiers, id1, id2, id3 semicolon. Of course, even it may be the syntax, it is the syntax error, it might be the syntax error, but it might be, and but not the lexical error. Fine, it's not a lexical error, that's sure, but check whether it is syntax error or not. Now how many tokens? 1, 2, 3, 4. So 4 tokens will be produced. Okay. Now what we have understood, how to recognize the tokens. While recognize the tokens, do not forget comments may come, spaces may come, ignore them, but it is the job of lexical analysis to identify. And whenever you see lexical error, like something which is started with digit, but after that you see some alphabet letters, then it will produce an error. Okay, this is one kind of lexical error. What is another kind of lexical error? In case if you want to see another kind of lexical error, somehow you did like this, int x, you started the comment, it started, but you did not end anywhere. Then what happened? The lexical analyzer is trying to look for the end rule. It's begin, right? Now it's trying to look for the end. Where is that end? Not happened. So no end pattern for the comment. No end, right? That end is not happened. No end of comment. So that is the reason it knows, the lexical analyzer knows I am producing an error. So something is missing in lexical analysis, so it will produce a lexical error. Got my point? So here error happens. Lexical error happens here. Okay. Similarly, there are a lot of lexical errors. You just think about it. But for the exam point of view, you have Very, very easy questions. Hardly you see 5 questions in throughout 30 years of the gate. You see just 5 questions from the lexical analysis. So you just learn the concepts and have the basics, like finite automata is used in this, or regular expression is used to design this finite automata, and how to recognize the tokens, what are the lexical errors, what type of tokens you have, that would be sufficient. And what is the symbol table, what it stores. Fine. You want to practice some of the gate PVQs, yeah, you have very simple questions, but do not practice the Fortran or some other programs. Before few years, before I think 15 years, you have other programming language in the gate exam like Fortran. So they were asked one question, find out number of tokens in Fortran statement. We don't need that. Okay, don't practice. Now it's to find the number of tokens in the following C statements, because as we have today the C in the syllabus. Now how do you find? Very simple. Printf is one token. Okay, so T1, and then we have the open parenthesis T2, and then you have this whole thing is considered as a 1 because it's considered as a string. Anything you mention in the double quote is called as just string constant, one token only. Okay, remember this. And not only this, if you cover in single like this, it's just called as a character constant. If you specify anything in single quote, just single quote, it's a character constant. They are single tokens. That's why all together, even you have a lot of things inside, but just considered as a one token. And then comma you have here, it's a T4, and you have I, it's T5, and then comma, it's a T6, and here ampersand I. Ampersand is an operator, I is identifier. So both are two different tokens here. Okay, I'll just keep here T7, and then I, it's T8, then closed parenthesis T9, then semicolon T10. And come here, you don't have anything, right? Total how many tokens you have? Just scratch check if I count anything is wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total you have 10 tokens. Okay. In case if you have any syntax mistake in this line, just ignore it, because we are not looking for the syntax, we are only trying to group the tokens. In case in future they will gently ask a question, I'll just mention that too. After print, in case you see the space, then you have something like this, right? Then what do? You just consider print is identifier and F is another identifier. You just count here 2, not 1. Okay, don't assume that they have done mistake in the gate question. No, they might be asking intentionally, how do you count the tokens? So here printf is the one token, but here print f, two different tokens, because space will separate the tokens. Okay, remember this point, 1, 2, and you have a 3, 4, 5, 6. Here you have 6 tokens. Okay, just variation. When you have already one question, then you should expect some other question with a little bit variation. In a compiler, keywords of a language are recognized during which phase? Very simple, right? In parsing, you do generating parse tree by looking at the syntax, right? But here lexical analysis is the right option. This phase only will recognize the keywords of a language, not only keywords, any kind of token, right? Like identifier, operator, constants, punctuations, all done recognized by lexical analyzer. Fine. The lexical analysis for a modern computer language such as Java, you may use C or something like that, needs the power of which one of the following machine models is or in a necessary and a sufficient sense. Necessary and sufficient means a strict form, and that's enough basically. Okay, actually if I don't have a sufficient word here, if they ask only necessary, right, all are necessary here. If you ask me, anybody can be used. but necessary and sufficient, the finite state automata. Here looks like all are correct, because if finite automata can do, then others can do, because they are more powerful machines in theory of computation. Deterministic PDA, non-deterministic PDA, Turing machine, these three are powerful than finite automata. If finite automata can do, these three can do. Finite automata able to design, you can use for designing lexical analysis, it means all the three can be used. Okay, but when the word is necessary and sufficient, then this would be sufficient. You don't need this three just to implement the lexical analyzer or just to design lexical analyzer. So this is one of the interesting and time taking question, but once you know the concept that I have already discussed, you can easily do it, right? Use the longest prefix rule and read each and every statement what they have mentioned, and you need to follow their definition, right? What you learn and what you study might be different from this question, but this question everything is given. It might take 2 to 5 minutes, but you should spend the time. Okay, so let me start doing it. What are the options we have here? I'm very sorry for the options, but okay. The question is about which one of the following is a sequence of tokens, right? Here you should have the sequence of tokens, and we'll find the sequence of tokens here. Okay. They might give some of the sequence like T1, T1, or T1, T2, T1, something like that, T3, T3, or none of this. It could be none of this. Actually, options are different. You can look at gate PYQ question. Now, how do you how do you analyze this data? Read the question carefully. As I told, everything is mentioned. That means you need to focus on the data, not on your knowledge. Your knowledge, we will apply it, but don't bring your knowledge directly without reading the data, because you did not aware that question mark, what is the meaning of it. Because I never read even in compiler somewhere except in regular expressions, right? If you want to implement lexical analyzer, you will see this code, but while preparing the gate, you don't. Now, a lexical analyzer uses the following pattern to recognize the three tokens T1, T2, T3, right? So there are three tokens. I used to represent always, right, T1, T2, T3, T4, because that is how we understand the code. Now they have given some pattern, don't worry about it. They have mentioned the x followed by the question mark represent means 0 or 1. If you study theory of computation, 0 or 1 occurrences of x means here the x question mark means it's just like epsilon or x only. That's the meaning. Epsilon means 0 occurrences, x means 1 occurrences. If you want 2 occurrences, double x, x followed by x. This is clearly mentioned 0 or 1 occurrences of the symbol x. Then whenever you see that this one, you can simply say epsilon or a. And r is the, it is mentioned anywhere, not required, because this slash represent, it's a bar represent the b plus the r only, star a. Now you got to know what is that question mark represent, right? You can write everywhere epsilon plus b, a or c whole star b, and then epsilon or c, b plus a whole star c. This is how you got to know what is this question mark representation. Note also that the analyzer outputs the token that matches the longest possible prefix, and you need to look at always longest possible prefix. We'll see that again. The string is clearly mentioned here, whatever it is, and is processed by the analyzer which one of the following is sequence of tokens, its output. So there are some options, and definitely one of the options only correct, because you are following longest prefix match. Okay, if you have more than one option also, we will see it. That's anyhow should not be when you implement a compiler. Now this is the key point for you. I'm just writing here b a. Okay, I need spaces also. b a and c, a b c. Okay, this is your input, or this is your program. You can assume that is your program. You can assume that is your program. Sorry. How many tokens are there? 3 tokens. Anybody can match, right? But who will be matching the longest prefix? Now you need to focus on 3 things. T1, T2, T3. You don't know exactly who is going to be the longest, but you need to look at who is going to generate the longest one. If any of these 3 is producing our entire sequence, then that is only the possible token produced. Right? But we don't know, right? Let's try. T1, how long it can produce this string as a prefix. Now let's try. B, can you produce epsilon B? Yes, you can produce. Second B, can I produce? Yes, BB. Can I produce this A? Yes, but this A I can't produce with this. I can do here B, B, A up to here only. See that? Second A I can't. I can produce 2 B's from here because of star is there. I can repeat twice. Then once I go to this A, other A I can't produce from this option. Okay. So B, B, A, that's the longest that T1 can produce. And T2 now. B I can produce here. Another B if I want to produce, I have to go here. If I go here, I can't come back. So BB, that's the longest one I can produce with the T2. That means T2 definitely not going to be the first token because T1 already showing the longest. Okay, now let's go to T3. Go to T3. B, I can put epsilon here. I can take B here, and another B I can take from here only. A I can take from here. A I can take from here, and C I can take from here. See that? Epsilon B, B, A, C. I can produce up to here. That means till this point we have just T3. First token is produced. Looks like when you look at the option, nobody matching because in the exam they started with T3 somehow here. Okay, the first option they have taken T3. Okay, so then you had a confusion which option is, because many options are having the first token is T3. So that's the problem in the GATE exam. Okay, anyhow, don't look at these options right now. And now let's move to the next remaining. Again it will start. Now look for T1, T2, T3. Who is going to be the longest one, right? That is very important. A, B, C, can I have here? A, B, C. I can, but I should end with A. I'm not proper if I can't generate A, B, C. I can generate A, B, C, A. See that? That A, B, C, even though I have till here, but I am not complete because this A need to be there. See, if you look at here, I stopped here because the T1 was ending with A. But now this one, I can generate what ABC till here, but without ending with a T1 is not correct. So T1 can't generate at all. ABC is not possible. What is possible? A, B, C, A is possible, but I don't have A there right now. So I can't generate ABC with this expression, right? It can't generate ABC. What can generate? ABCA. Remember that. Part of the string only it can generate, that doesn't mean that whole T1. Okay, next one, epsilon A, B, but that can generate AB but not ABC. So this one I can generate A, B. It's okay, may be correct or may not be correct, because after that if T3 can't do it, I will take T2 because that's the longest. Now T3, A, if epsilon I take here, A, B, then C. Now complete T3, A, B, I'm properly ending with C also. This A, B, C I can generate. So now this is also T3. So one of the option you will see T3, T3. That's going to be the right option. T3, T3. Now T3, T3 is the right answer. That's all you need to do. If you can do it properly, how to start and what is the longest prefix match? I have 3 rules, 3 patterns. Then which one is going to match longest? Then that will be considered as a token till that point. After that, again, all the tokens you are trying to match, who will match next? Okay. The answer is T3, T3 is going to be the right option for this. T3, T3. Fine. Sometimes they may ask how many tokens are produced in the sequence? 2 tokens. T3 followed by T3. That's it. So in overall, in this introduction as well as in in lexical analysis, it's very easy. That is just how many types of tokens. Focus on this, the whole lexical analysis will become easy. And then what is lexical error and what is symbol table, and finite automata, regular expression used to design lexical analyzer, phases of compiler, 5, 6, 7, and you should know how to use these words. Basically looks like 6 words, but you have the 7 phases in a sequence. Okay, phases of a compiler. And then if you know some of the errors, you should know the error handler, and you have written lexical error. In other chapter I'll talk about syntax and then semantics, so on. Now this is about the introduction as well as the lexical analysis, what we have learned. The one point while recognizing the tokens, learn what is that maximal munch rule, longest prefix matching. You should know this rule, longest prefix matching rule. Okay. And thank you so much for watching this video patiently, and we are going to learn the next lecture, which is parsing and syntax analysis. Very, very important for the whole compiler. Sometimes you see all the questions only from the syntax analysis. So I believe that you are following this lecture, and thank you so much. See you in the next lecture. Bye bye. Take care.